Warm greetings. Today's topic is we'll see the continuation of the second chapter until electrostatic potential of for a dipole visa. So we are going to see from equipotential surfaces. Okay, so we'll see how the potential is equal. Right now, before that, I will give you the mind map for the first lesson, electric charges and fields. Here you can able to see all the uh, sections, what all you have learned, and all the formula as a summary in one page. This is the more advantage of mind maps. So it is very easy and useful for you. So we consider mind maps. So mind map, it breaks a chapter into a structured visual format. That is for grade 12 board exams and competitive exams, like JEE, NEET, IACR, and then ICAR, whatever it might be. Mind map acts as a quick revision tools. Okay, and instead of reading full chapter again, you can revise the entire concept in minutes. For example, it's a powerful visual tool, we can say, that help you organize concepts and connect ideas and revise faster. Okay. So you know that for grade 12, where concepts are vast, interconnected, mind maps make learning simpler and more effective. This helps students to understand the big picture and improves memory retention also. So it involves formulae, key points and applications, etc. Okay, so we'll come into this. See, actually, what is the main purpose of the electric charges and fields? So everything is given here. If you want, students, you can take a screenshot, or if you want this PDF to you, let me know from the message. So you can text through the message like mind map chapter number 1 physics, or mind map electric charges and fields. Then I will send the link to you. Okay, then so we'll move on to the rest of the chapter. So we'll see now equipotential surface. So this is all about equipotential surface. Equipotential surface means we can understand it is a surface over which potential has a constant value. So that is equipotential surface. Okay, it has the constant value. Okay, so what is that particular constant value or in everything? So we are going to derive how the equipotential surface and what is the relationship between electric field and the potential. Everything we are going to see further. Right now, we'll see if a charge is moved over an equipotential surface, the amount of work done in moving the charge is zero. That is the case. See, for example, in your book, it is given an equipotential surface is a constant value of potential. It says if the charge Q, the potential is given by. So this is the potential. And then equipotential surfaces of single point charge are concentric spherical surface charged at the, centered at the charge like this. So that means the potential is same. So it is actually inversely proportional to radius. Or we can say the potential is radial. So if you say around the charges wherever the potential is same, like that it will be, these are all the equipotential surfaces. Okay, or spherical surface which is centered at the charge. So this is nothing but it is the electric field. You know, electric field is radially outwards. Then the potential around this particular R, it is same potential throughout the sphere. So here it is same potential throughout the sphere. Here it is same potential throughout the sphere, like this. Okay, so electric field is like this. And then you are going to derive a relationship between, so already it is derived, the relationship between the potential and the electric field. That and all we are going to see. It's very interesting topic. Okay, for a point charge, the equipotential surface will be concentric spheres. We saw at the location of the charge. Equipotential surface and the electric charge E at a point are mutually perpendicular. I've told you, no, this is the potential and equipotential surface. If you take that as a plane, if you take this as a plane, Three planes are equipotential surface and the electric field are perpendicular to it. Okay. So the direction of the steepest decrease of potential is in E. That means what is the direction of the potential, equipotential surface? So it says, right, the direction of the steepest decrease of potential is in E. That means it goes on decreasing like that. The steepest decrease of potential it may found in all the subsequent plan if it is in the direction of electric field. Then spacing among equipotential surface is the reason for the regions of the strong and weak field. The spacing is done to address there is a strong field and the weak field, okay, locations. So we can say these are all the spacing and then the spacing, it address the strong and weak field location. Okay, that's what it's given here. I told you no work is required to move a test charge on the surface. That means no potential difference between any 2 points on the surface. It is known as equipotential surface. By definition, we can define it like this. Okay. Okay, so it is normal. Okay, normal means plane normal through the x-axis means perpendicular. Okay, so equipotential surfaces are perpendicular. Okay, and then we'll see now. And these are all the equipotential surfaces. Okay, two identical positive charge here. Okay, this is positive charge, this is positive charge. Okay, this is a dipole unit. That means two equal and opposite charges. Okay, both positive and negative charges, equal and opposite positive and negative charges, like that. Okay, equal and opposite identical charges. That is a dipole, which is separated by a small distance. Its equipotential surfaces are defined in this picture. And then it is positive, right? Both are positive charges. There might be deflection in it. So its equipotential surface is defined in a picture. And then it is very clear for you. And then this is talk about the relationship between field and the potential. So what is the field we are going to take? One surface. This surface potential is V. Okay, and the another surface, its surface potential is V plus delta V. That is, what is V plus delta V? I can able to say. Okay, V plus delta V means there is a small difference in potential, and then within the distance between these two will be delta L. Okay, the plate A, like that we can take. Okay, potential surfaces. This is the surface A, surface B. Okay, you are seeing the potential at the point P. There is a distance between both the surfaces. That distances will be delta L, and there is a potential difference. So VB is, what is VB? It is the work equals the potential difference. What is that? What is how the work is equivalent to the potential difference? Everything you have learned in a work energy theorem, right? Potential difference is nothing but it can be equivalent to the potential energy difference. Everything we saw in the initial portion. So VA minus VB is nothing but the difference in potential. Okay, that is equal to the work done. Okay, so work done is equal to given. See here how it is given as work done E modulus into delta L. You know that force time displacement is the work done. Okay, the force can be written as E, right? E into Q. Okay, Q is the charge, we can say, if you are considering a point charge or unit positive charge. Imagine that a unit positive charge is moved along. So that means this Q is equal to +1. If you say Q is unit positive charge, it is +1. So you can remove this. So F can be written as E into Q. If Q is unit positive charge, we can substitute 1 here, then it will be E. What is E now? E is F. Okay, that means electric field due to a unit positive charge can be expressed in terms of like this. Into dl will be the potential work done. or the potential difference, it is a work done, we can say. So work done is VA minus VB. This is the first surface. This is the second surface. So V minus V plus delta V, that is equal to minus delta V. Okay. As I've told you, the work done is always negative, so that the work is done against some force, or we can say against the Coulombic force, right? So it is negative. So minus delta V by delta L. Yes. Okay. So minus dV by delta L. If you are taking dV as magnitude, then you can neglect the minus. So you can write delta V by delta L. So we can say V is equal to E into R. Like that also we can say. This R is nothing but the length difference, or the length, the distance between two surfaces, two equipotential surfaces, we can say. Here it is given as E into dl. Okay. So we can say electric field is in the direction in which the potential decreases steepest. That's what I'm saying. Electric field, what direction it is? In which the potential decreases steepest, sorry. So the potential decreases steepest, there the direction of the electric field is. So its magnitude is given by the change in the magnitude of potential per unit displacement normal to the equipotential surface at the point. Okay. Suppose if you are considering magnitudinally, so we are taking E modulus is equal to delta V modulus by delta L. They are saying for unit displacement. So what is unit displacement? It is equal to 1. For a unit displacement, its magnitude is given by whose magnitude? The potential and the electric field magnitude is given by the change in the magnitude of the potential. That means electric field magnitude is change in the magnitude of the potential. Okay. And these two are normal to the equipotential surface. That also we saw. The electric field is normal means perpendicular to the surface, equipotential surface. Okay. So all these, hidden concepts you had to learn. This is the major relation between. So E is equal to delta V by delta L, or delta V is equal to E times delta L. So this is the major relationship between E and V. Okay. Then system of charges, as usual, potential energy you have to find out. So this expressions I will teach you. First, you have to take for the position vector. This is charge Q1 and Q2. There is a potential energy difference between these two. So with the distance R1, 2, you can write the potential energy as like this Q1, Q2 by 4 pi epsilon naught R1, 2, right up. And then we can say it is between Q1 and Q2. That Q1 and Q2 may be greater than 0. That is, the electrostatic force is repulsive. Okay, and a positive amount of work is needed. If it is repulsive, the work is positive to be done against this force to bring the charges from infinity to a finite distance. For unlike charges, these two are like charges. Q1, Q2, when it will be positive, both are positive charges, like charges. For unlike charges, one is positive, another one is negative. Opposite charges, the forces are attractive. Electrostatic force is attractive. So a positive amount of work is needed against the force to take the charges from the given location to infinity. In other words, we can say a negative amount of work is needed for the reverse path. Okay. So the potential energy is negative, we can say. Likewise, if you are taking three particle system, can you able to understand? You have to analyze the concept in this manner. You are considering Q1 and Q2, and then it is at the distance R12. You know, this is what? It is the position vector. Okay. Already we have learned about this position vector. This is position vector. You are taking some origin of reference. From the origin of reference, you have to consider this as R1, this as R2. R1 is the position vector from this origin. Here the point, here the charge Q1 is present. Okay, R1 is the position vector. If you take it in 2-point system, so x1i plus y1j. Okay. or we can say x1 comma y1 point. Here x2 comma y2. Here, okay, x2 comma y2 or x2 I cap plus y2 j cap. So what is this R12? R12 is the resultant. Resultant will be R2 minus R1. Okay. So anyways, you should reverse the R1 vector. Okay, and the resultant will be like this. Okay, the resultant direction will be like this. Clear? So this and all we have seen already. It is R12, okay, for two particle system. How can you take this? Q1, Q2 is the matter. If these two charges are like charges, that is both positive or both negative, definitely in between these two experience, either positive charge, that is attractive force or repulsive force. Got it? So this attractive force, I can say, if the forces are repulsive, then the work done is positive. Positive work is done. Positive amount of work is done. Okay? So, in order to overcome the repulsive force, suppose if Q1 and Q2 are attractive force, that is one is positive, another one is negative, then we can say it is attractive force. So, negative amount of work is needed for the reverse path. Okay. So that means from infinity to present locations it will be. So the potential energy is always negative. Okay. Is it clear for you? So here, if the amount of work is needed, so all of you take down the notes from this. This is very important point. Okay. All of you take down the notes. If Q1, Q2 is greater than 0, that is potential energy is positive. You can write in your notebook. Q1, Q2 is greater than 0. Potential energy is positive. Okay. So Q1, Q2 is greater than 0 means in the bracket itself you can write like charges. Okay. So electrostatic force is repulsive. So repulsive force. Repulsive force. Okay. And then here what will happen? Work done is negative. No, positive, right? For greater than 0, positive amount of work done is positive. So it brings the charge, you can write now, brings the charges from infinity to a finite attractive. So our finite distance apart, we can say. We saw, right, P to R to P. If you brought the unit positive charge from infinity to 1 point. Okay. Infinity to a finite distance apart. Have you written? The same way, you have to write Q1, Q2 is negative, all vice versa. Okay. There, the reverse path, that means from infinity to the present locations. Okay. So the potential energy is negative. Is it clear for you? Then, from this equation 2.22, we can take, okay, it is generally easily generalized for a system of any number of point charges. Suppose if you are taking Q1, Q2, Q3, like this. Okay. To bring Q1 from first from infinity to R1. You are bringing Q1. We don't know Q1 is where. So you are bringing Q1, okay, from infinity to R1 position. So we don't know where the R1 is. Here, the 0, origin of reference. So this might be the R1. Okay, this might be R2. This might be R3. You can draw, then only you can able to understand how it is. This is R3. Okay. This is R1. Clear for you? Okay. Since it is the distance between R12 and R13, it is R23. Okay, so right now we are going to write work done in this particular step. Okay, Q2 has achieved the potential of V1 of R2. Right up? V1 is the potential of Q1. It is experienced by the charge Q2. Okay, at the radial distance R12. Clear? So at the radial distance R12. So Q1, Q2 by 4 pi epsilon naught R12 we can write. Okay, so what is V1 of R12? Q1 by 4 pi epsilon naught R12. What is V1 right now? V1 of R2 is Q1 by 4 pi epsilon naught R12 into Q2. Okay, is it clear? Then Q1, Q2 produce a potential which at any point P is given by. So this point, any point you can take. So at that point, the potential is first V1, comma V2. If you consider any external point P, then you have to show Q1 divided by R1P, K Q1 by R1P, K Q1 by R1P plus Q2 by R2P. Clear? So this is the potential. So work done next in bringing Q3 from infinity to R3. Q3 is brought from infinity to R3 position. So Q3 times V1 comma 2 you have to take. So here it is Q2 times V1 of R2. Here Q3 times V1 of 2 at R3. So V12 at R3 we can take. So here also you have to take this. Okay. Okay, then K into Q1 Q3 by R13 plus Q2 Q3 by R23. So both will be taken. R13 and R23. Okay. So the total work done in assembling the charges, how the total work done will be. If you are taking U is the potential energy is the total work done. If you are taking all these three, then it will be R12, R13 and R23. Right? You can take all the total. So 2.23 plus 2.25. Okay. So this is the characteristic of the present state of configuration and not the way the state is achieved. So the experiencing potential, electrostatic potential of each and every charges and its potential difference is derived right now. Okay. Is it clear for you? I have shown how it is. Okay. So you just have a look, go through it. So examples you can learn. Suppose if you have any doubts, let me know. This is after this, it is given potential energy of a single charge. It is very easy. You have to take Q is very small. And I told you, no, Q into V of R, that is the potential energy. Already we saw, right? So potential energy is Q into V of R. Okay, electric field in terms of potential will be R into V. Or some distance L into V. Okay, like that. Okay, so this is the potential, electrostatic potential and electrostatic field. This is the potential energy difference and the electrostatic potential. So it is the major relationship between these two. And go through it. Suppose 2 point charges. Two charges means, so already we saw Q1 is already there. It experiences V of R1. Okay, Q2, you have to, for Q2, you have to multiply this. Okay, so that is the formula we have already seen. Work done or potential energy. Then you should add these two, Q2 V of R2 plus this one. So this is the work done in bringing Q2 to R2. So the total potential energy system will be starting from the 1. Q1 V of R1 plus Q2 V of R2 plus like this. It goes on like this. Okay. Like this, you can write for three charges, system of 3 charges, system of 4 charges. So you can write, this is potential energy. So far you have seen here, okay, this is all about what? It is potential energy of a system of charges. So here the charges are, I mean, surrounded and it is randomly oriented. So there must be n number of charges, system of charges. So for that, you have to consider three charges and then, so it is written two charge system and three charge system. Here it is two charge system, here it is three charge system. Okay. So like that you have learned. Okay. The major difference between these derivations are, I will explain you. Here you have written for potential energy in an external field. Okay, so what is the major difference? Field also influencing in it. Jesus. So Q, what is Q? You know that you are taking the charge from infinity to one point. That Q is the unit positive charge. Okay, so you have to in consider the electric field also here, like this. So here also the potential energy of system of two charges in an external field. Everything in an external field. In an external field, I will compare and give you. In an external field, see what is the potential energy of system of two charges? This in an external field. Okay. First, we calculate the work done bringing the charge Q1 from infinity to R1. So work done in this step is taken like this. Then equation 2.27. Next, consider the work done bringing Q2 to R2. In this step, work is done not only against the external electric field, but also against the field due to Q1. So you have taken Q2 of V of R2. Okay. So against the field due to Q1 means it is that Q1, Q2 by 4 pi epsilon naught R12. Likewise, you have to find out all the distances. Okay, by the superposition principle, you should add, okay, against the two fields. Okay, so here the thing is, no such an external field is, we are considering here. Here, so work is required or work is not required, like that. Okay, so your charges may experience, if there are like charges, what is the work done? If they are unlike charges, what is the work done? If you consider the three particle system, okay, Q1 is first brought from infinity to R1, but no work is required. Okay, so why it is no work is required? Initial, it is the starting. First charge we observe. So next we bring Q2 from infinity to R2, that is with reference to the first charge. Okay, so work is done starting in that particular step only, not in the first step. First step, it is already there. The Q1 is, you found the Q1. You are assuming that the Q1 is coming from infinity to that point. So that work is already done. We don't know about that. So that we are saying no work is required for that. For the second charge, we are taking the work done as like this. Then the charges Q1, Q2 produce a potential. Potential, work done in moving charges from one point to another point. That is the potential. Okay. So that you know. And then what else I can say? One second. So this is the major difference. Okay. So from the Q2 only you are just recording. You are calculating the work done. Okay. From Q2. Okay. So likewise Q3 and Q4 all depends upon first Q1 and Q2 and Q3, all interdependent, okay, based on this picture we saw. Okay, so it's clear for you. Then can you handle that? Yeah, then I will let you know. Just a call. So we can proceed with the next one. So students, you must understand the question, right? Potential energy in an external field, we are now seeing. So before that, not you have considered the potential energy as the work done. Okay, not in an external field. Okay, initially. Now it is the potential energy of a dipole in an external field. Like the same what we have seen in the, you can correlate with electric dipole, torque on a dipole. Okay, you know this, right? So twisting force. Like this, the same, you have considered the dipole in the external electric field.